driving cars, space exploration, and etc. For example, here is a video of Tesla in autopilot mode using its various cameras and sensors to drive completely on its own. This is similar to what we are able to accomplish with our robot. Okay. Now that you know a little bit about robotics, let's move on to the rest of the content. So we will first explain what first tech challenge or FTC is.
Yuvraj, yeah. So professor just called. They've disconnected. So please hold for a second. They're reconnecting.
Okay. Did they see the video or no?
Yeah, it's okay. I think you can start from the outline of today's when they give us a go. Okay, Yuvraj, they're on. You can back up a little bit and start again. You said.
From where?
Yeah, back up more. I think from introduction to robotics would be good. Yeah.
So first, I will talk a little bit about what robotics is and where it can be used. Put simply, robotics is the process of using engineering and computer science to create robots, which can come in many different forms. The most common use of robotics, accounting for 30% of all industrial robot installation, is the automotive industry. Here, robots are mainly used to speed up the manufacturing and assembly process. Additional uses for robots include robotic surgery, combat drones, autonomous driving cars, space exploration, and others. For example, here is a video of a Tesla in autopilot mode using its various cameras and sensors to drive completely on its own. This is similar to what we are able to accomplish with our robot. Now that you know a little bit about robotics, let's move on to the rest of the content. We will first explain what First Tech Challenge, or FTC, is. Then we will give a brief overview of the complex robot we have built and how it accomplishes the tasks we were given. Then we will take a look at our design and engineering process, which consists of a fully computerized model of our robot iterations, as well as a close-up look at each of our robot's subsystems. Furthermore, we will take a deep dive through our software development process. We will explore the algorithms and tools we use to accomplish fully autonomous operation of our robot. These include computer vision and autonomous pathing. Finally, I can answer any questions you may have. What is FTC? First Tech Challenge is a robotics program that challenges teams to design, build, and code robots to compete against other teams at local, regional, and national competitions. Each year, a new challenge is presented to teams with various tasks to be completed in order to score points. The better a team's robot is able to complete said tasks, the more points they will be able to score. We will give a short overview of this year's challenge and the tasks associated with it. So here is a diagram of the game arena for competitions. Today, we will be focusing on the section in the top right corner. At the top, there is a warehouse filled with blocks and balls that the robot has to pick up. The black bars are barriers, and we have engineered our robot to be small enough to go around the side of the barriers. The robot is only allowed to pick up one freight at a time. Once this is done, the robot has to go back and drop the freight onto the red shipping hub. This movement is essentially repeated throughout the match in order to score as many points as possible. A cycle is defined as one pickup and delivery of freight. This term will be used throughout the day. Here is a video example of a robot performing some cycles. In this case, the robot is being controlled by true drivers. They are using video game controllers to control different parts of the robot and telling it to complete various cycles.
YouTube. One minute. Nope, you don't have any. No. 30 seconds. You have to be a little bit more careful now. 15 seconds. 15 more. 10. 9. 4. 3. You can get one more. 2. 1.
Now, I will talk to you a little bit about our intake design. So the term intake refers to the process of taking game elements, primarily the blocks and balls, into the robot in order to manipulate them to score. This can be done through many ways: wheels, tubes, zip ties, etc. As seen on the slides, we utilize spaced out tubes to create a finger-like system which allows us greater manipulation of the freight. On our robot, we utilize a coaxial intake system powered by one servo and one motor. We drive this using a worm gear powered by another motor. This allows us to move our intake 180 degrees from left to right. We also utilize Lexan, the clear material displayed in the images to allow higher visibility when we intake freight. Also pointed out by the image, we implemented a color sensor to detect when the tubes have managed to intake a freight, which allows us to run a set of pre-programmed instructions, allowing us to score the freight we intook during the autonomous period. On the other hand, the term outtake refers to manipulating the game element after intaking the element to score it for points. On our robot, we use 6 sets of Bisumi SAR 220 ball bearing slides mounted at an angle 27 degrees above horizontal. Ball bearing slides are commonly found in drawer assemblies and use ball bearings for linear motion. They are composed of 2 metal slats and have aluminum balls between them, providing motion. We utilize a fully custom 3D printed claw designed in Onshape, a CAD software that we printed in 3 separate pieces and assembled with 4 screws. Again, we utilize a second color sensor to detect when there is a piece of freight within our claw in order for our robot to execute a series of pre-programmed instructions during the autonomous period. Additionally, we used some custom parts that we did not simply buy from online. They were mainly 3D printed and CNC machine cut. Our robot is roughly 80% custom, and we either 3D printed or machined out of aluminum and polycarbonate from our designs in CAD. Our team owns 3 3D printers, which allows us to rapidly prototype and test iterations and print final designs. Due to a shortage of FTC pre-made parts from suppliers, we learned to 3D print replacement parts, prototype quickly, and to manufacture and implement custom parts we designed in Onshape. We used a variety of 3D printing materials, which we chose based on their properties and our certain needs. Now we will move on to software development. We used Android Studio to program in Java for our entire season. Additionally, we set up a GitHub repository so that we could implement version control, share code easily, and always have a backup of our code. This allowed us to roll back to a previous version in case we made a mistake or lost our code. One of the tasks in the autonomous mode is to detect the position of a team element in one of 3 positions. As you can see on the floor, the cup is currently in the left position. We have a camera on the robot that we use to detect which position the cup is placed in. As you can see on the floor, there are 3 possible spots that the cup can be in. Based on which spot the cup is in, the robot has to drop a block on a certain level of the shipping hub. If it is on the left, you have to drop it on the bottom level. If it is in the center, you have to drop it in the middle level. And if it is on the right, you have to drop it on the top level. Your team gets bonus points if it is able to detect what spot the cup is in and drop the block onto the correct level. This all happens automatically while nobody is controlling it. So computer vision is a field of AI that uses algorithms to process images captured by cameras into data. They can be used to collect color values and objects or detect motion and find objects when paired with AI. In robotics, computer vision is used to detect certain conditions in the robot's environment and then respond to those conditions using the robot. We used OpenCV, an open source CV library, during the season to detect our custom shipping element on the barcode positions. Using our webcam, we took in color values from different sections of the field to find the shipping element. We used the format YCBCR to process our camera frame. Y stands for luminance and represents the brightness aspect. CB stands for blue difference, meaning how far a color is from blue. And CR stands for red difference, or how far a color is from red. Each of these components is a live feed that you can take values from. We take the CB value, which is the distance of a color from blue, to determine where the shipping elements are by comparing the collected value with the color value of the other square. Whichever square has a significantly different color must contain our cup. Because our camera was only wide enough to view 2 out of 3 barcode positions, we used a process of elimination to determine that if we cannot see the shipping element at all, it must be in the undetectable position. Here is a little code segment that is capturing the CB value from the 2 viewing areas in the camera frame. It creates the 2 viewing rectangles and then takes the average CB value from within those 2 areas and stores them in the region 1 and region 2 variables. These 2 values get processed later on to decide where the cup is located. So now that you know how our computer vision works, I will talk to you a little bit about our autonomous pathing, which is basically controlling where your robot actually moves around the game area. So our main algorithm is Roadrunner. Roadrunner is an open source trajectory building library that allows us to define a set of constants based on our robot design and then move to certain locations on the field based on those constants and drive encoder values. Roadrunner uses PID, a type of closed feedback algorithm, to automatically correct for pathing errors encountered by the robot, making our autonomous consistent and resilient to change. Roadrunner also employs a set of trajectories and presets that allow our robot to move accurately without overcomplicating our code or making use of high and expensive sensors. So here is a short video explaining some more aspects of our autonomous mode, as well as the entire 30-second autonomous sequence.
Welcome to the Equilibrium.exe Team 19458 Freight Frenzy Control Award presentation. During autonomous, our robot can be placed in one of 2 starting positions, one closer to the warehouse and the other closer to the carousel. Demonstrated on the video is our green line autonomous, where the robot automatically delivers 4 additional cycles of freight into the Alliance shipping hub. Through the use of Roadrunner displacement markers, the robot is able to perform other tasks while moving on its trajectories, such as extending the outtake slides. The robot is able to use the Roadrunner library to automatically correct for trajectory errors in additional cycling. The robot also utilizes a color sensor in the intake to see if it has picked up any freight during cycling. At the beginning of Autonomous, the robot uses OpenCV pipelines to automatically determine the position of our custom team shipping element on the field, scoring bonus points for delivering freight to the corresponding level of the Alliance shipping hub. The robot performs a comparison on color values contained within the highlighted red boxes on the camera site to accurately determine the position of the team shipping element by measuring the average color distance from the color red. Our team shipping element is colored green to accentuate this effect. Through driver control enhancements like intake macros, the drivers are able to easily maneuver the robot to drop and collect freight. The robot's intake and outtake are optimized to easily collect all types of freight and deliver freight to the high and middle levels of the Alliance shipping hub. Thank you for listening to Team 19458 Equilibrium.exe's Control Award presentation.
So next, we can show you a full match video of our team competing in the semifinals at our regional robotics championship.
Welcome to the Equilibrium.
Yeah. Okay. This is the full match video.
Ready.
Let's get it started in 3,
2,
1, go!
So our robot is on the top right, and our partner team is on the bottom right. We are competing against the robots on the left.
and the robots are off.
We got some motion over on the red side, reaching over, depositing yet another one. We're going to spin a duck here on the red alliance. What's happening on blue? Ooh, look at that stack over on the blue side. 2 blocks, one on top of the other. And folks, this is just the beginning. This is not even teleop yet.
All right, it looks like Almond Robotics was successfully able to place 2 to 3 blocks in their autonomous
Drivers,
period.
pick up your controllers.
So far,
3,
red has the lead,
2,
102 to 74,
1.
but that's just the preliminary score.
At the end of autonomous, it's 138 to 98. Those are some of the highest autonomous scores we have seen all day.
Well, Spare, what are you going to expect? This is the best of the best competing here today. Blue is the first to score on this shared hub. Red quick with an answer, but not enough to tilt it into their favor.
Meanwhile, on the blue lines, we see team 5421, Armed and Dangerous, working on the Alliance hub, whereas the Almond Robotics team is working on the shared shipping hub. They currently have lead of the shared.
Yeah, but don't forget about 19458 reaching all the way up there to drop off another one into the top of their Alliance-specific hub. 2818 is continuing to drop blocks into that shared shipping hub, still not quite enough to tilt it into their favor.
The scores are getting super close, despite the difference in autonomous. It's currently 156 to 158, and the blocks keep on being collected and keep on being deposited.
All right, these hubs are getting full. These warehouses are getting empty. These are some really fast robots.
We got about 10 seconds left until endgame. And that's when we'll see teams starting to go towards ducks and start trying to cap.
All right, we got some flashing lights over on the red robot. That's those functional LEDs that Sapir was talking about earlier. We got some ducks getting spun on the red alliance. What about blue? Looks like we got a cap attempting to happen on the red alliance. G-Force drops it on, and that is a good cap on red.
We got 5 seconds left.
Here it comes.
3,
2, 1, over!
So as you can see, we definitely won that game. And yeah, if I didn't mention before, this was at our regional robotics championship. So
Ready.
Let's get it.
thank you so much for joining us today. If you have any questions, feel free to let us know.
So Professor Manin, if students have any questions, we can take the questions now.
Hello.
Hello. Yes.
Hello. Stop कर दो ना.
Hello.
आज मैम. हेलो. मैम नहीं. आप एक स्टूडेंट दूसरे कह रहे हैं कि आप इसका जो एक पीपीटी हमें सेंड कर दीजिएगा. एक्चुअली उनको थोड़ा ऑडिबल इसलिए नहीं है, थोड़ी फ्लिकरिंग थी ना ऑडियो में. नेट का इशू था हमारे यहाँ, तो इस वजह से. मैंने वीडियो है तो क्लियर हो जाएगा. तो सेंड कर दो. हाँ जी मैम है, फोटोज में आपको सेंड कर दूँगा.
Hello, Yuvraj.
Yeah.
Yeah, so yes, the professor just spoke to us. He called and they said, yeah, they don't have any questions right now, but they would like to get the recording as there is some audio issue also there. So they would like to get the recording and they'll follow up with any questions they have. So we'll be in touch with that.
Yeah.
All right.
Okay. How do